Is AB 2015 AP exam question number 3. It says Johanna jogs along a straight path. For t between 0 and 40 inclusive, Johanna's velocity is given by the differentiable function v. Selected values of v of t, where t is measured in minutes and v of t is measured in meters per minute, are given in the table above. Okay, it says use the data in the table to estimate the value of v prime of 16. So let's see what's going on here. So what I did is I just plotted these points here, the points of the table. Time is always going to be on the x-axis. That's always the independent variable. And so I plotted those data points on the x-axis. Now, what does v prime mean? V prime is the slope of v. So we want to know the slope of this function here at time t equals 16 minutes right here. Okay, now we don't know what this function looks like. I mean, it could go but we do know it goes from here to here. It could go up here, it could go down here, it could go straight, whatever. Now, whenever you want to find the slope at a certain point, if it's not at a given point or if it's not given to you, then what you want to do is use the 2 points closest to it on either side, because that would be the most accurate. So what we want to do then is find the slope here. Like I said, the curve could go up here this way, it could go down here. We're not sure, but the simplest way to do it, and they're all approximations, we might as well just do the slope of the line from here to here. So if you're just going to do the slope of the line, whatever the slope of this line would be the slope of the velocity at that time 16. So you just go ahead and do, so it's going to be slope of a line is going to change in y over change in x. So here's what you have here. It's nice to write it out. It's the velocity, the acceleration, v prime is the acceleration at time 16 minutes is going to be v of 20 minus v of 12. That's a change in y over 20 minus 12. That's a change in x. And then just go ahead and plug the numbers in, and you get 5 meters per minute squared, which is an acceleration. This is velocity over time is meters per minute, which is meters per minute squared, okay? And here's what they gave you the points for. They only gave you 1 point for the approximation. Make sure you use units in these kind of questions, because you don't know whether they're going to give you points for them or not. They usually do give you points for units in 1 or 2 questions. Part B says, using correct units, explain the meaning of the definite integral of the absolute value of the velocity in the context of the problem, and approximate the value of this definite integral using the right Riemann sum with 4 subintervals indicated in the table. Okay, so let's see what we do. So now, when you do these kind of questions too, it's a good idea. Always roughly plot your points to get a visual of what's going on. So here's our 5 points. I plotted those here. Now it says, let's just do this part first. It says using 4 subintervals. Well, it's always works out very nicely. If I did 4 subintervals, if I broke them up, in other words, each point, just draw a vertical line, and that's what I'm going to do here. They're my partitions or subintervals. So here's one subinterval from this point to this point. There's the next one. Here's the next one, and here's the 4th one. So they're either partitions or subintervals, okay? And then it says use right Riemann sums. So in this first subinterval or first partition, I go to the right side, go to the point and draw it across and form a rectangle to where this other partition is, okay, or vertical partition is. And then in this interval here, I go to the right side again because it says right Riemann sums, and draw the height of the rectangle over to this piece of the partition, this vertical partition here. Same thing here. Go to the right side, which is the point down here, and draw it over to where it hits the other end, the left side of the partition. Go over here, this subinterval, right side, draw the height of the rectangle until it reaches the left side of the partition. Okay, so there's my rectangles. And so there's my 4 rectangles or 4 subintervals. Okay, and then there's the areas of those rectangles. Now, this says the definite integral, so we're doing approximation. A lot of times in these kind of questions, you can't come up with a continuous, nice function. So what we do is take data points, and then we use those data points to just make approximations to various things like this. So by doing this now, taking the area of these regions, this is a definite integral of an absolute value. So it's going to be, the areas are all going to be positive. So if I just look at it, the base of this rectangle right here is 12. That was from the intervals. Remember, when this goes from 0 to 12, 12 to 20, and so forth. And the height of these subintervals, it's right sub, right Riemann sum. So the height of the first rectangle is 200. The next height is 240 minus 220 and 150. So now, so the area of the rectangle, this would be 12. The height is 200. So I just multiply those. And this one here, going from here to here, from 12 to 20 is 8. And the height was 240. This one goes from 20 to 24. And the height, it goes down to minus 220. But these are areas. And that's what the definite integral of the absolute value means. It means it has to be positive. So therefore, this becomes, we make it just the area of this rectangle, which is 4 times 220. And this one is going to be from 24 to 40, which is 16. The height is at 150. So we have to add up all those subintervals. And that would be what this is. And this is going to turn out to be 7,600 meters. And again, notice looking at units, the area under these curves is going to be, the height is going to be meters per minute. The base is minutes, so base times height, meters per minute times minutes. The minutes go out and we get meters. So that's what the area under the curve is. It's in meters. And now let's get a feeling for what the meaning of this means. If you understand velocity, if velocity is positive, if this particle is moving along the x direction, if it's positive, it's moving to the right, and if it's negative, it's moving to the left. So it looks like in these regions here, the velocities are positive, which means it's moving to the right. In this region here, the velocity is negative, so it's moving backwards. But it's still moving a distance. So if I was just to integrate right across here without the absolute value, this would be positive, positive. This would be negative. This would be positive. That's basically your displacement, okay? But we're looking for distance because no matter which direction I move, if I move this way for this amount of distance, and if I move backwards, it's still a distance traveled. So that's why the absolute value of the velocity is going to be a distance traveled. And that's what this definite integral means. So the meaning of this is, the absolute value of a definite integral of velocity is the total distance and in meters that Johanna jogs for the 40 minutes. Whenever you answer these kind of questions, it's over a certain time interval. Make sure you state the time interval and make sure you include the units. And there's the points we get. We get 1 point for this explanation, and I'll guarantee you got to have the time interval in there. Okay, you got 1 point for using right Riemann sums. That means basically that the heights were 200, 240, 220, 150, and then 1 point for the approximation. Part C says Bob is riding his bicycle along the same path for time t between 0 and 10 inclusive. It says Bob's velocity is modeled by this function b of t, where t is measured in minutes and b of t is measured in meters per minute. Okay. It says find Bob's acceleration at time t equals 5. So let's do a little thinking, and I want to go over, review some stuff here, and we'll talk about units, because units are very helpful a lot of times, okay? So if I look at velocity, velocity is the derivative, or x prime, it's the derivative of position, okay, which is the same as dx dt. X prime is the same as dx dt. X is like, let's say it's measured in miles, and time is measured in hours. And so the velocity would be miles per hour, which is true. That's a velocity. Okay. Acceleration is v prime of t, which is the derivative of velocity with respect to time, just another way of saying the same thing. And velocity is miles per hour. Time is hours, but I'm writing it as hours over 1, so we can see the next step a little simpler. So what I have then is I have miles per hour, I invert multiply times 1 over hours, and I get miles per hour squared. So that's an acceleration. So you see how going through these steps, I get the proper units worked out. If I go the other way, velocity is the definite integral, or the integral of acceleration with respect to time. And so acceleration is miles per hour squared. Time is hours, and I wrote it as hours over 1. So if I multiply these, one of the hours goes here out with this hours, and I get miles per hour, which is a velocity. And position is the integral of velocity with respect to time. Velocity is miles per hour. Time, dt, is time, which is in hours. The hours go out and I get miles. So you can see how if I get a little confused, if I look at units, I can sort of get myself on the right track. Okay, so let's see what we're looking for. In this question here, we're looking for Bob's acceleration. So if this is his velocity, that's going to be the derivative of this function, and we want to know it at time t equals 5. So we're looking for b prime of 5. So let's get a little visual. Now again, this is not a calculator question, so you wouldn't be able to draw this function here. But so this is give you a feeling for what's going on here, though. I graphed the velocity function. That's what this is. This is b of t. And here the slope of this, so I did a little sliding tangent, and the slope then is the acceleration. So you can see, so this is b prime of t. Wherever I am here along the t line here, that's the velocity, the acceleration. So you can see over here where the velocity is going down, the velocity is negative, the acceleration is negative, therefore the velocity is going down. And over here the acceleration is positive, therefore the velocity is going up. This has nothing to do with speed. I'm just talking about acceleration and velocity here. Okay, so it just gives you a little idea what's going on there. So if I want to find now b prime of 5, then I would just say, well, I have the b of t is equal to this function they gave us. So b prime, you just differentiate, and the derivative of a polynomial is just going to be, this will be 3t squared minus 12t, and then derivative of a constant is 0. So if I want b prime of 5, I just plug in 5 for t, and if I plug in 5 for t, I get t squared is 25 times 3 is 75. 12 times t is 60. You subtract it 15, and the units of acceleration in this case are meters per minute squared. Now, just to show you over here on this, I can move it to time t equals 5, and that's at t equals 5. Here's the slope of this function. By the way, another way of looking at this also is the slope here. Then the slope of this tangent line here, the slope is change in y over change in x. And in this case, the change in y is meters per minute divided by change in x, which is in minutes. So meters per minute would be meters per minute squared, which is also acceleration. Here's how you get your points. You got 1 point for getting b prime of t or using b prime of t, and then 1 point for the actual answer. Okay, part D says, based on the model B from part C, find Bob's average velocity during the time interval t between 0 and 10. Okay, so I want to do a little review on that too, because average value formula can be confusing. We can forget it. It's one of those things, if you memorize it, you're going to forget it or get confused. If you try and understand it and develop it, I think you can get it right every time. Okay, so here's a picture again. I'm just going to show you a picture, and we get the average value formula from the mean value theorem for integrals. And what the mean value theorem basically says is that the area under some curve, so the area under this function here, and is b of t in this case, and the area under the function, I can approximate the area under that function with some rectangle. So you see here, if I kind of play around, if I'm trying to get this blue region equal to this red region, because then, see, the area of the green and the red is under the function, and the area of the green and the blue is under the rectangle. So when these two are equal, the area under the rectangle would be approximately equal to the area under the curve. If I get them exactly equal, then it would be exactly true, okay? So I don't know where it is, but I'm just going to play with it. So just to give you a little feeling for that. So that's the mean value theorem. It says the area under some curve is equal to the area of some rectangle, using the distance of the same base here, 0 to 10 in this case. Okay, so that's how we develop the average value from there. So here's the area of the rectangle. The area of the rectangle is equal to the area under the curve, so that's pretty simple to remember. Okay, mean value theorem for integrals has to do with integrals, which is a net signed area, which is areas, okay? So the area under the rectangle is going to be the height of the rectangle, which is wherever this rectangle, the top of the rectangle hits the curve. That's what we call f of c. It hits it at time t equals c, and that's where it is. And b minus a is the base of the rectangle. So base of the rectangle times the height of the rectangle is equal to the definite integral under this function. Now I'm just doing general terms under f of any function. This is just some general function f, okay? And if I was to take and divide both sides by b minus a, this f of c, that's the same, that's f average. And so what f average is the average height of this function here. In other words, if I want to find the average height of this function, see this function goes from 350 here, well it goes a little below 350, but it goes up to about 700 or so here. So the average height is going to be somewhere between, say, 300 and 700. Okay, it's going to be below this value right here, which is about 260 or something like that, and it's going to be between here and here. That's going to be the average height. Okay, and so that average height is when I get the area of the rectangle equal to the area under the curve, when I get these two regions, the red and the blue regions of equal size, then that would be the average value. And you can see in this case, I did it for this function b of t, it's approximately 361, okay? And again, 360 is between the lowest value on the function and the highest value on the function. Okay, so let's go see how we do this now. So now let's apply this formula. We want to know the average value of the velocity. So now what I'm doing is taking this formula and just changing it to this specific function. So the velocity, so b of c times the base, so this is the height of the function, times the base is equal to the definite integral of the velocity function. And then by dividing by b minus a, which is 10 minus 0, which is 1/10, this is b average. This is the average value of that function. Okay, or in this case, it's the average velocity. So it's 1/10, the definite integral from 0 to 10 of the velocity function with respect to time. So let's go. Now, let me show you units too, by the way, because people sort of get confused with this a little bit too. Let's look at the units here. This is b average. Remember, this is a velocity. So if I look at units, b minus a is in time. So this is 1/minutes. This is a velocity, which is meters per minute. dt is in minutes. So if I work this out here, minutes go out and I get meters per minute, which is the velocity. Okay, so something sort of to remember here. If I want to know the average velocity, in this case, which is the average of b, I need to integrate b. Okay, that's a good thing to remember. The average of b is the integral of b. The average of f is the integral of f. Okay, so to keep that in mind. So now we have to go the steps for this thing. So the next thing to do would be to integrate this. So here I am here, right? And I got the integral. So now I have to take the integral, and this is a polynomial, so it's a pretty straightforward integral. So it's 1/10. The integral of 10 to the third is 10 to the fourth over 4. The integral of 6t squared is 6t cubed over 3. I like to do this division later. If you try to do two things at once, sometimes you make little mistakes, and there's no need to make little mistakes. And the integral of 300 is 300t, and that goes from, the limits are still from 0 to 10. Then I got to plug in 10 first, and then plug in 0. So when I plug in 10 to the fourth over 4, this becomes 2, and then 10 to the third, and then this becomes 300 times 10. And then when I plug in 0, if I plug in 0 into each one, t is 0, t is 0, t is 0, so I subtract 0. Now I have to do this arithmetic here. So it's a pain in the neck, but it's not that complicated. This is whatever, 10,000 divided by 4, and this is 1,000 divided by 2 times 2, and this is 3,000, and then just add these up. Don't forget to divide by 10, and you get 350 meters per minute. That's your answer. Now see if I can move this over here. If I move this to this is the average value. This is the average height of this function right here. Okay, and if I move this to the average value, right over here is the average value. This is the height right here. You can see that this blue region it looks very close, but it is exactly the same area as this red region. That would be the average value. And here's what you get the points for in this question. You got 1 point for the integral. So 1 point for setting up this integral right here. And you got 1 point for the antiderivative. So 1 point for taking the antiderivative and 1 point for the answer. Now again, always make sure when you're doing these when you do AP questions, good idea to look at their answers, because this way you know what they're expecting. I've been giving to you pretty much the same exact way they have, but there's little things. So here's what they give you the points for, and there's what they expect to see. And so learn to look these things over, because you could lose a few points if you don't answer them exactly as they would like to see them.